Hello, everybody. I'm very delighted to be here. And let me get started with the talk. So, as you can see, the title of the talk is on some informational aspects of the noosphere and beyond. And what I'm going to be talking about are, how does some of the work that I do connect to the noosphere on Earth, but also perhaps potentially on other worlds as well. So let's get started with some preliminary. So you will be hearing this word a few times in the rest of my talk, so I think it's only right that I define it, which is the word astrobiology. Astrobiology, as you can see, is the study of the origin, evolution, distribution, and future of life in the universe. This interdisciplinary field requires a comprehensive, integrated understanding of biological, geological, planetary, and cosmic phenomena. So here we can already see several overlaps with the vision of Teilhard de Chardin. For example, the notion of the lithosphere, the atmosphere, the biosphere, and the noosphere all interacting with each other, as well as the concept of cosmic evolution, a theme that stretches back about 13.7 billion years ago. So that's, of course, one field that I want to mention. And one might ask, what are the primary objectives of this field? Well, there are three of them in all. The first is, where did we come from? How did life originate on Earth and in other worlds beyond Earth, perhaps? The second one, are we alone in the universe? Which is there extraterrestrial life out there? And the third one, whither are we going? Quo vadis? What is the future of life on Earth and beyond? And now let's go to the concept of the noosphere, which of course we've already heard several definitions from Terry and so on. So here I reproduce the exact text from Teilhard's famous work, The Phenomenon of Man. So basically, one can understand the noosphere as a particular biological entity such as has never before existed on Earth. The growth outside and above the biosphere of an added planetary layer, an envelope of thinking substance to which, for the sake of convenience and symmetry, I have given the name of the noosphere. Now, this is particularly relevant for the next part that I'm going to tell you, because note the emphasis on the thinking element. So obviously, human beings and their ability to think and to come up with ways of interacting with the world around them and also simplifying their modes of existence came up with technology. So this brings up another concept which is very closely intertwined with the noosphere, and one that, in some ways is directly linked to the fate of the noosphere, which is the technosphere. So the technosphere has many different definitions. I provide one here by Jan Jaslewicz, which is the technosphere encompasses all of the technological objects manufactured by humans, but that is only part of it. It comprises not only just our machines, but us humans too, and the professional and social systems by which we interact with technology. So one thing to note here is that, especially in this new era, known as the Anthropocene, we've been seeing, the technosphere in particular, but also the noosphere expanding substantially in complexity. There's been this acceleration of various activities that some of the speakers have already spoken about. So I want to show you two such examples that I find very striking in how this great acceleration has come to take place. The first is Mars. You all know, of course, that we have forests, that we have animals, all kinds of stuff, many living beings on Earth. So one can add up the total amount of biomass, and then we can compare it with the amount of anthropogenic mass, which is mass that has been processed by anthropogenic activity in some form. So one can compare the two of them and see how the two of them stack up against each other, which is what this plot over there shows. And what this plot indicates that sometime in the early 2020s to mid 2020s, the total amount of anthropogenic mass is going to exceed or has already exceeded the amount of biomass on Earth. And the amount of biomass on Earth is not a small amount by any means. The y-axis essentially shows the amount in trillions of tons, which is 10 to the power 15 kilograms. So it's a very high number. So we see one example of how the technosphere is essentially, becoming comparable to the biosphere in this regard. Now, for one more example, one can look at the amount of energy consumption that is taking place. One can ask, what is the energy consumption of the biosphere? Well, the biosphere, as we've said before, is really a very large and intricate network. So it makes sense that it takes up a lot of energy to sustain itself. So one can look at the power utilization of the biosphere. This was quantified quite recently, for example, in Höhler et al. And what they find is that it requires an energy sustenance of about 2,800 terawatts. So a terawatt is 10 to the power 12 watts, and as you may all know, the watt is the unit of power. All the bulbs that we see have a certain power associated with them. And then what about the technosphere, or basically looking at all the activities that humans perform? We can ask, what is the energy consumption associated with anthropogenic activities? And the answer for that turns out to be about 20 terawatts as of 2020. So it's slightly outdated, but not by much. So you can see that the power consumption by humankind is actually lower than that associated with the biosphere, but not by a whole lot. And given the fact that currently energy consumption is growing exponentially, it is not unfeasible that at some point these two quantities are also going to become equal to each other. So I've spoken about two different, very fundamental things that we all can intuitively understand even from the time we are children. One is the concept of mass, comparing two different types of masses, and then comparing two different types of energy consumption. But then what about the third member of this trifecta, which is information? That is something, we will look at now. So that brings me to the topic of information transmission on Earth, and what are some of the results I'll be showing in this context. So we all know, of course, that information transmission is very valuable for humans. So we see one very well-known example of human communication. Of course, hopefully this is not how it usually happens, but we can see one such example. So we have already heard in a very nice and very insightful talk by Terry as to how language played a really fundamental role in making us human, and then we've heard from Jacob about the role of culture in that regard. And in both those cases, these two phenomena enable human beings to achieve certain things that they would not be able to achieve individually. There's this notion of collective intentionality and so forth. So we can see that the ability to exchange information, to convey information from one agent to another is really profound. But one thing to note is that, of course, in the case of language, humans have an extremely high degree of sophistication. But what is sometimes overlooked is that the fact that information transmission and communication is a ubiquitous feature of life on Earth. So I want to give you one of my favorite examples in this regard in a microbial realm, which is something known as quorum sensing. So here we see an overview of quorum sensing. You can see that there's, so basically imagine that you have a cell, and then the cell begins to produce these molecules known as autoinducers. Now, these autoinducers are essentially signaling molecules. We see one example of such a molecule, which is something known as an acyl homoserine lactone, which is depicted in the plot over there. So basically, imagine that these molecules are being released. Now, let's say that this particular cell is embedded in a larger population of cells, all of which are also performing the same behavior. At some point, because there's so many molecules that are being emitted, at one point what happens is that the concentration of these molecules outside becomes more than the concentration of molecules inside the cell. And so what happens in that case is diffusion, where you have these molecules migrating from higher concentration to lower concentration. And when that happens, the cell senses that instead of the concentration of these molecules dropping because they're being pushed out, it actually starts to increase. So that tells it something. It tells it that, oh, there's a lot of, I have a lot of my kin around me that are doing a similar thing. And that in turn, because it comes to know that it's in a population, this can actually enable it to change what one may call its behavior in many different ways by expressing certain genes, by turning certain genes on and off. So here we see an example of how quorum sensing can lead to very different behaviors as opposed to the case where you have only isolated cells or only a few cells. For example, one can have biofilm formation take place, one can have the secretion of certain chemicals that act as pathogens, and so on and so forth. So the virulence is something else also that can be modulated by quorum sensing. So here too, we see the role of information, in the biosphere, and how, information is in some sense being transmitted from one member of the species to a different member. But that's not just all. So we've seen before about two humans communicating with each other. Now we see examples of two bacteria, in a sense, talking to each other. But then it can also go across species. So here we see an interesting example of how a whole array of signaling mechanisms can lead to the exchange of information between plants and then certain microbes. So when it comes to trying to understand how to model these things, there has been a very well-developed theory for a very long time, which goes back all the way to 1948, to Claude Shannon's theory of mathematical theory of information, and this particular area is known as information theory. And here we see a schematic of how people model communication in that particular area. So one has essentially a transmitter, and there's an information source which then relays its information to the transmitter, and then the transmitter essentially conveys this information to a receiver, and then this information that is transmitted to the receiver and then be acted on by the receiver in some form as well, and that can lead to some feedback as well. Now, the latter part we are going to ignore, namely the feedback, but basically, in essence, we have the transmission of information starting from a transmitter, passing through a certain channel, which is a certain medium and a certain modality of sharing this information, and then moving to a particular receiver. So this particular modality matters a great deal, as does the medium in which it occurs. For example, language is something that we speak, so it essentially travels through air in the form of sound wave. When we look at quorum sensing, we saw that the agents of information, the carriers of information, are the signaling molecules, the autoinducers. So there you have the diffusion of these molecules happening through various media. It could be air, it could be water, and so on. So in that context, some of the work that I've done tries to understand, how the medium can play a big role in mediating the amount of information that can be shared. And this is something that has implications for not just various environments on Earth, but also several environments beyond Earth. So I will return to this particular theme a little bit later on. But what I want to talk about is something else, which is we basically spoke about how one could compare mass in the biosphere and in the technosphere. We also spoke about how You could have energy consumption in the biosphere and in the technosphere that are being compared. So now let's look at the role of information. We've seen so far that information is indeed being transmitted in the biosphere, and clearly we know that information is flowing in the technosphere as well. So human-to-human communication is one example, but thanks to the presence of the internet, one has so many other forms of communication as well. There's human-to-machine communication, and moreover, there is machine-to-machine communication. In fact, some people have estimated that machine-to-machine communication may have exceeded or will soon exceed the amount of other modes of communication in the technosphere in the 2020s. So, what we did was we tried to do an estimate of how much information transmission was happening in the biosphere and in the technosphere. And this is the paper that was published a few months ago. It was selected as a research highlight by NASA. So you see the press release that is associated below there. So this brings up the question, which is as follows. With the information in the biosphere and the technosphere. So that's the paper that I'm going to talk about a little bit. But before I do so, I think it's incumbent on me, to also highlight some of the caveats, because this is a very complex topic, as I'm sure one can imagine, and therefore it is, it's good to spell out some of the limitations that exist. So the first thing to note is that the biosphere is vast, as is the technosphere, and in the case of the biosphere, microbial communication is not very well understood, especially in the so-called deep biosphere that exists underneath the surface of Earth. So there's many known unknowns as well as possibly unknown unknowns as well. The second thing is that we use a heuristic approach, something known as an order of magnitude approach for those who would be familiar. The third thing is that we only quantify the bulk aspects, namely, we quantify what is the total amount of information flowing, in the biosphere and in the technosphere. Therefore, what you really have is an emphasis on quantity, but not really on the quality. So, in other words, not all information is going to be equally useful for an organism. Only some of it may actually affect its viability in some form. So, there are certain semantic aspects to that which are not considered here. And that interplay between quantity and quality is very important, because one can have the transformation of quantity into quality and vice versa, as is well known in the social sciences. So, to summarize, this is basically, meant to be a preliminary foray, as we said in that paper. With those caveats, all the results that we have can be embedded in that one plot you see over there. On the x-axis, what we have is the time that has lapsed starting from 2019, and on the y-axis, which is the main quantity of interest, we have the total amount of information that is being communicated, which is expressed in units of bits per second. So many of you, would be familiar with what a bit is. If you have some variable that can take a value of 0 or 1, there's an information of 1 bit associated with that. And so you can look at how many bits per second are flowing in the biosphere and in the technosphere. So what we find over here is that, if you have a relatively short time scale, the amount of information flowing through the biosphere doesn't change a whole lot. So that's why the dotted line is more or less straight in time. On the other hand, stretching back to more than 20 years, there's been a very rapid increase in the amount of information flowing in the technosphere. In fact, it's been doubling on a time scale of every 3 years or so. So the findings can be summarized as follows: that firstly, we estimate that the information transmission rate in the biosphere as a whole, under actually conservative assumption, might be around 10 to the power 24 bits per second. So that's 1 trillion bits per second. And again, this is in some ways a conservative estimate. It could even be higher. The second thing is that we compare this rate with the amount of information that is being transmitted through the entire technosphere as of 2020 2, and what we find is that there's a difference of about 9 orders of magnitude. In other words, the information flowing through the biosphere is actually about 1 billion times more than what is in the technosphere as per this preliminary model. Now, that is a striking divergence because we saw energy and mass before, and in the case of mass, we spoke about how the two of them were nearly equal to each other in the 2020s. And then if we looked at the amount of energy that was flowing, that was being used by the biosphere versus the technosphere, what we found was, what others have found is that it's only about, the amount in the biosphere is only about 100 times more than that of the technosphere. Whereas when it comes to information flow, on the other hand, there does seem to be potentially a wide gap. Now, the third thing one might ask is we spoke about this great acceleration that's happened in many quarters, for example, in the context of anthropogenic mass being generated, in the context of energy consumption by humankind. So one might ask, well, if one has exponential growth, when would the amount of information flowing through the technosphere become comparable to that of the biosphere? And so for that, if one makes the assumption of sustained exponential growth, which can be debated and is certainly an assumption that one makes, well, what we find is that the technosphere would actually catch up with the biosphere in less than 100 years from now. So right now, the gap is very large. It is 1 billion times smaller, but because of this exponentially growing rate, the gap is diminishing quite fast. So I want to again sort of end this part by reiterating the caveats that I mentioned earlier. And now I just want to talk a little, to sort of go a bit beyond Earth and then, try to place some of these results in a broader context. That's because, as I mentioned at the early on, I work primarily in astrobiology, which is concerned with life beyond Earth as well. And so I just want to briefly talk about how these concepts of the technosphere, the noosphere, and so on, and the infosphere, which was a concept that Terry mentioned, how these could also relate to other worlds as well. So, for example, I spoke about how one of the work that I did tries to understand using the tools of information theory, concepts such as the Shannon-Hartley theorem, the concept of mutual information, etc., to try and understand how is the information transmission rate in microbes being modulated by the environment itself. And that could have a significant bearing for where and how life originated and how it evolved, because certain settings might be more conducive for the flow of information than certain others. So here in this plot, there's 4 different cases that are considered. The first are basically lakes, oceans, seas, etc. on the surface of Earth. The second are these very specialized environments that exist at the bottom of the ocean, which are sort of underwater volcanoes known as hydrothermal vents, which are considered to be very promising sites for the origin of life. And case 3 describes the lakes and seas that are present in Saturn's moon Titan. Now, Saturn's moon Titan is very interesting because it happens to have not liquid water, but oceans of liquid gasoline in a sense, because most of the oceans and most of the lakes and seas are composed of liquid methane and liquid ethane. So it's not liquid water. The temperature is incredibly cold. It's around minus 180 Celsius. I don't know exactly how much that is in Fahrenheit, but know that it's much, much colder than even the coldest places on Antarctica. And then the last one is I also looked at how information transmission could happen in air as opposed to happening in water. This is something again that has a bearing on some worlds within a solar system where life has been theorized to exist in aerial settings. So here we see that there are quite significant differences in the amount of information that can be transmitted as a function of the separation between two microbes, the transmitter and the receiver. So that's the x-axis, the separation between two different microbes which are doing the signaling. And then on the y-axis, we have the amount of information that is being transmitted in units of bits per second. So that was in the context of a potential extraterrestrial biosphere. Now, what about potential extraterrestrial technospheres or noospheres? So, for some of you who might be interested in this field of the search for extraterrestrial technological intelligence, or people who like sci-fi in general, you might have heard this particular term come up. There's something known as the Kardashev scale, which was proposed by Nikolai Kardashev, a Soviet astrophysicist in the 1960s. And what he said was, well, if there are extraterrestrial civilizations out there, then he suggested that, well, maybe one could go about classifying them based on their energy consumption. So again, in that particular case, the emphasis was on energy. And so here we see the three different Kardashev classes that are present. So the first one is the Kardashev 1 civilization, which essentially can capture all of the energy that is falling on the surface of the planet, which is being supplied by the star, and it can harness that energy for various purposes. And then the Kardashev 2 scale talks about being able to harness all the energy of the star itself, which is many, many orders of magnitude higher than what humans can do right now. And then there's even more, which is a Kardashev 3 society, which is something that can essentially harness the entire power of a galaxy. And so when people search for extraterrestrial technological intelligences, they often tend to use the Kardashev scale as a benchmark or as a guiding or as a guideline to try and talk about what kind of societies they are looking for. And here is one more example of that, which also illustrates the close connection between the size of the society, the spatial extent of the society, the amount of energy consumption associated with the society, as well as the complexity, which of course is a hard concept to define. So basically, the notion has always been that higher energy is correlated with higher complexity, which in turn is correlated with higher spatial spread of that particular society, and so on. But then, so this is my closing thought, that many extensions to this scale have been proposed, and they have also revolved around some kind of energy manipulation or energy use in some way. But then, as we have seen, the concept of the noosphere and the technosphere, bringing other dimensions beyond just the crudely material ones. So we go beyond mass and energy. Information, for example, is one such entity. So perhaps one may also start to think about, trying to classify these kind of putative societies, based on what kind of information flow is associated with them and how much information they are able to process and handle. And so the last thing I would say is that when it comes to trying to understand where humankind is headed, of course, we've seen that there are all these trends that are emerging in the context of how much mass is being processed by human activity, how much energy is being consumed by human activity. And now one can add information to that, because obviously with the growth of internet, the Internet of Things that is emerging, and so many other trends, AI and so on, understanding the role of information transmission in the noosphere, the technosphere, becomes of paramount importance. But then, as I've said in the last few slides, it could also be a concept that could perhaps help us refine some of the aspects of the search for extraterrestrial technological intelligence. So with that, I end my talk, and I guess Jacob and I will be happy to take questions. Thank you.
These are wonderful talks, and of course they're so very smart, but I want to voice a concern. And the concern is that when we look at either nature, biological nature, or culture, what we find are little islands of functional organization, something that might qualify as an organism, in an ocean of other processes in which these islands are participating, but those oceans are not themselves functionally organized. And so the kind of analysis that's called for anything that qualifies as an organism, whether it's a cultural organism or a biological organism, is different than the kind of analysis that's called for vast aggregates. For example, in biology, an organism or a species highly adapted to its environment is different than a population of those organisms or an ecosystem composed of those organisms. And what I find is, in these kinds of analysis, is an insufficient awareness of what we're talking about. Are we talking about something which is functionally organized, or this larger aggregate? What I find is that the conversation and the analysis kind of toggles back and forth between them without realizing that, at least in my view, that there's a very different style of analysis. And in a practical sense, what we need to do, if we're going to have any kind of noosphere that in the Teilhardian sense, is to basically to work towards a whole Earth and everything underneath it as like an organism. So it's a very important question, and I just wanted to raise the whole issue. I'm raising a very large issue for Terry and for you and for everyone in this audience. Thank you.
Yeah, that's a wonderful point. Thank you very much for bringing it up. I absolutely agree. And in fact, one of the third caveat that I mentioned is sort of related to that, which is when you look at two coarse-grained quantities, you run the risk of sometimes, overlooking some of the finer details. And the second thing about islands, that's a very important point. The great physicist John Wheeler said that, we essentially have these islands of knowledge submerged in an ocean of ignorance. So I think there is that, that fine-grained structure there. And indeed, one of the things that fascinates me is this whole theory of island biogeography, because what we really have are these knowledge islands that are, in a larger pool that are not connected. So absolutely. I think there's a lot more work to be done on that front. Thank you.
A question at the interface between your talks, about the power of computational large language models. One for you, Manasvi. When our computers are using up so much energy to generate information, where does the information world and the energy world converge in a space that you're concerned about, that we're going to burn ourselves up generating more information? And the question to you, Jacob, which I think is related, is you showed Turing and the matter of Turing degrees and the matter of the computational power and the unsolvability of problems. Do you see that there's something about the noosphere that will extend something about the level of Turing degrees we can challenge by creating these models, particularly if we put Shoggoths in the middle, which I think was brilliant.
Peter, that's really, you bring up a very important point, which indeed I didn't talk about because, of course, time constraints and so on, which is the relationship between energy and information itself, and how efficient is that across various systems, like whether it be microbes in the biological world or computers and so on. And one of the remarkable things is that when it comes to carrying out computations, there is an energetic cost associated with it, which is known as the Landauer principle, which gives a lower bound on how much energy is needed. And it turns out that cells perform computations very close to that lower bound. So in other words, they can generate a lot of information for a given amount of energy, whereas computers, on the other hand, are comparatively vastly more inefficient. There was, in fact, a Twitter post by Jan LeCun, who some of you will know as one of the pioneers of deep learning and so on, which points out that fact that a computer, for instance, would require he says, about 100,000 times more energy to generate the same amount of information compared to the human brain. So yeah, there are those interrelations as well that I didn't speak about, but that's certainly a very important point. We do discuss it in our paper, but I didn't cover it in the talk. And that's because when it comes to computers, a lot of the energy is not being used to generate information as such, but is being dissipated away in the form of waste heat and so on in the circuits and the hardware associated with it. So there are certainly some very non-trivial connections between the two, that do exist.